Howdy, students. This is Unit 13, Reaction Rates and Equilibrium. Today we're going to cover a couple of videos, and each one's going to be broken down. The first video here is going to cover activated complex, and we're going to look at energy and how energy affects the rate of reaction. And then later down, we're going to talk about rate laws and how to write rate laws, which govern how fast reactions can occur. So the first thing we're going to look at is the word rate. Rate is a measure of the speed of any change that occurs within an interval of time. You can have rates for all kinds of things. In chemistry, we're going to look at the rate of how fast a chemical reaction occurs. So the reaction rate is the change, and we're going to look specifically at concentration, the concentration of a reactant or a product per unit time. So this wouldn't be miles per hour. This would actually be concentration, which is molarity, capital M, moles per liter, and how that changes over a given amount of time. Some reactions go very fast, like burning, combustion. Others go very slow, like rusting and oxidation. In order to understand how speed is governed, we have to look at the collision theory. So in order to react, two or more particles must collide with sufficient energy, which we call the activation energy. And if we have the proper molecular orientation, we can also get the reaction started. If the colliding particles do not have either of these two, then no product is formed. So bottom right picture here, little man pushing the boulder. It's going to take some type of energy to reach the top of the hill. However, once we reach the top of the hill, the reaction can proceed, the boulder can proceed without any additional work. So we call the top of this hill the activated complex, where the activation energy is sufficient for us to start the reaction. Now, the bottom left picture, if we're looking at actual chemicals here, we might combine A2 and B2, and we get this unstable activated complex where a brief moment of time they're collided with each other, and then they decide if they have enough energy to reach the top of the hill in order to form A, B, and there are two of those. Now, sometimes they collide, and if they don't have the proper orientation, there's not enough energy required, and we call it an unfruitful collision because it does not work. It is unsuccessful. So let's go back to that activated complex. Also known as the transition state, it's the point at which the reactants can become products. We've reached the top of the hill. It's a high energy temporary arrangement of atoms that form when particles collide with sufficient energy. So we're going to look at a potential energy diagram for reactions, and this is going to be key for us to understand reaction rates. So the first part of the diagram would be the reactants here, which will always be on the left side of the diagram. The y-axis has free energy, and the x-axis is time. So once we reach the activation energy, which we call E sub A, we reach the transition state, which is the point in time at which we form the activated complex so that we can form products. So the top of the hill, this is our transition state, also known as the activated complex. So we're going to use these potential energy diagrams in order to answer a few questions. So using the graph below, what is the energy of each of the following? So what is the energy of the reactants? 80 kilojoules. Well, how do we get that? The reactants are here, always on the left. And if we look at where the line is, where our reaction starts, it starts at 80 kilojoules of energy. How did I know it was kilojoules? The y-axis told me here on the left. How about the energy of the products? Well, my final product resting energy is at 20. Okay, how about the activation energy? Now, this is going to be the activation energy of what we call the forward reaction, which is left to right. We're going to learn about equilibrium soon, and we can actually have a reversible reaction and go right to left. So the energy of the activation is when we start with the reactants and we push the boulder all the way up the hill, and we want to know how much energy that takes. So that's a difference from 80 to 100. And so we're going to take the absolute difference, and that would be 20 kilojoules of energy right here for the E sub A. The activated complex is the top of the hill. So if we look at the top of the hill, that's 100 kilojoules. And then what we're going to learn towards the end, we've actually looked at enthalpy before. This is delta H, the change in enthalpy. We have an equation to do this. We're going to learn it later, but it is products minus reactants. And we covered this in Thermochem in Unit 10. So if we do the products minus the reactants, that would be 20 here for the products and 80 for the reactants. If we do it in that order, we're actually going to get a negative 60 kilojoules, which tells me that this reaction is exothermic because it's a negative value.